Good evening. So Pedro and Nathan asked me to chair this last session. And maybe before we begin, Pedro or Nathan, do you have any announcement to make?
No.
No? Okay, so now we can move on. So the format is as before. So we'll have a presentation by discussion leaders. We have 3 of them. And then after that, we have a discussion, question to the leaders and also discussion among us. So I'd like to ask them to give a presentation in the order of Green, Schwarz, Witten. And so could I ask Michael to start first by sharing the screen.
Rosie, I think we decided that I would go first.
Oh, okay. Oh, if you, yeah, if that's the order you would like, yes, please go ahead.
Can you see my screen?
Yes.
So I thank the organizers for allowing me to participate in this amazing meeting. They've done a fantastic job. The title of our session is supposed to be Perspectives on String Theory, Past, Present, and Future. And at this stage of my career, I feel more qualified to discuss the past than the present or the future. I hope that these remarks will be of interest to those who do not experience this period. So I will quickly survey the distant past of string theory and mention some of the key developments that took place. The choices were tough and subjective. So, as you're surely aware, the bosonic string theory developed in the late 1960s out of S-matrix theory, which was being studied as a potential way of understanding a theory of hadrons, and starting with Veneziano's famous formula, and followed by important work by Fubini, Verrazano, Nambu, and a couple hundred other people. Since I want to emphasize the supersymmetric extension of bosonic theory, the first big blow was Pierre Ramon's formula for a free fermionic string. What he did was to find a string analog of the Dirac equation. It's a beautiful equation I like to call the Dirac-Ramond equation. A couple months later, Neveu and I constructed a second theory of bosons, and we quickly realized that our bosonic theory and Ramon's fermions fit together in a single theory, and demonstrating that was achieved together with Charles Thorne. It's hard to believe that this was over 50 years ago, and so much has happened in these 50 years, but it doesn't seem that long ago to me. A few months later, Gervais and Sekita wrote down a formula which for today maybe seems trivial, but was pretty amazing at the time. And it was simply a freeze action in 2 dimensions of bosons and fermions. And as you know, if you have the equal number of bosons and fermions, that's supersymmetric. But this was the first example in which someone wrote down an action and showed that it was supersymmetric, at least as far as I know. And this example motivated Wes and Zumina to construct 4-dimensional supersymmetric theories a couple of years later. And also the same year, Neveu and Scherk observed that in a suitable low energy limit, either the bosonic string theory or the RNS string theory reduces to Yang-Mills theory at low energy. And of course, that uses open strings with Chan-Peyton factors. In 1971, Claude Lovelace argued for the necessity of 26 dimensions for the bosonic string theory. This was a real shock to people because up until this work, everybody assumed that we were talking about 4 dimensions. Considering anything else was regarded as preposterous. However, that attitude quickly changed. The fact that the RNS string requires 10 dimensions was soon understood, and various no-ghost theorems were proved first for the bosonic string by Brouwer, Then by using a different method, Goddard and Thorne proved them both for both theories, and I used Brouwer's method to give an alternative proof to the RNS theory. In 1973, Yonea showed that general relativity emerges at low energy in much the same way that Yang-Mills does, but in this case, starting from closed strings. The following year, Shirk and I rediscovered Yonea's result, but we went further and proposed using string theory to construct a theory of all forces. This was a big conceptual breakthrough. It required shrinking our strings by 20 orders of magnitude. And we expressed optimism about the UV finiteness of the theory and the fact that in a theory of gravity, having extra dimensions could actually be beneficial. In '76, Shirk and I obtained N=4 super Yang-Mills, and we did this by first constructing 10-dimensional super Yang-Mills and doing dimensional reduction. Soon thereafter was the famous work of Liazzi, Shirk, and Olive, in which they explained the necessity of projecting the spectrum of the RNS string in such a way as to give a space-time supersymmetry. And they gave evidence for that symmetry by showing that there were an equal number of bosons and fermions at each mass level, but they didn't actually prove it yet. The following year, Crémière, Julia, and Shirk wrote down the amazing formula for the action of 11-dimensional supergravity. This was a real shock to me. It was completely unclear to me where this fit into the greater scheme of things. The following year, I spent a year in Paris working with Shirk, and among other things, we studied how to break supersymmetry in string theory by using twisted boundary conditions and so forth. And then in 1980, Joel Shirk tragically passed away much too early. It was a great loss personally and for theoretical physics. And as you can see from this slide, he was really a major force in this field. In late '79, I began collaborating with Michael Green, and Lars Brink also participated in some of our work. The first thing we did was to prove the space-time supersymmetry of the GSO projected theory. And then we formulated and named type 1, type 2A, type 2B superstring theories, computed various tree and one-loop amplitudes. In 1983, we constructed an alternative worldsheet action that instead of having two-dimensional supersymmetry made the space-time supersymmetry in 10 dimensions manifest. In 1984, we analyzed anomalies of the type 1 superstring theories, and we discovered that among all of the possible classically allowed gauge groups, only SO32 is anomaly-free. And we showed that E8 times E8 could also work, although we didn't know such a theory. And that was subsequently, of course, introduced by Gross et al., who found it first. So after a 10-year period in which string theory for unification attracted very little interest, the subject suddenly took off. Despite all the enthusiasm, there was also quite a bit of outspoken opposition to the subject. The main complaint, I think, was that it was far removed from experiment, which was certainly true. It's unfortunately still the case. However, as many very bright young people entered the field and amazing discoveries were made, string theory became mainstream. And this conference is a testament to its vitality. Thank you.
Thank you, John.
Over to Michael.
Can you see my screen?
Yes.
Right. So I have had a wonderful 2 weeks. It's been a fantastic conference, and I've been incredibly impressed by most of the talks. The organizers have done a great job in very difficult circumstances. They've set the standard for future conferences, and we will see what happens next year in Vienna. One of the problems with this presentation is that this conference shown, as always, that string theory has developed into a huge subject that encompasses ever-widening areas of theoretical physics and mathematics. So it's very difficult to present a perspective that does justice to all of its richness. So what I thought I would do is just compare the way in which string theory originated with its present state, because I think there are lessons to be learned. I will focus on one particular lesson that might be learned from it. So let me begin by saying that I was a postdoc in Princeton in 1970, and I was wondering how that might fit in with this talk. And then, of course, I realized that we're now 51 years later, and 51 is 3 times 17. 17 is a prime number. So I thought I would focus on perspectives as seen through a cicada rather than through my own eyes, since there are so many cicadas that have come out this year, and they were coming out in 1970 when I first went to Princeton. So let me begin by going back to 1970, and this will be the main part of what I have to say. So in 1970, let's imagine a very intelligent cicada emerging in Princeton after 17 years hibernating underground. So the cicada vaguely remembers being born in 1953, when there wasn't all that much happening, although at the time it would have seemed like there was an enormous amount happening. Quantum electrodynamics had been incredibly successful, and new particles were being discovered, in particular the mesons, and properties of the nucleons were being figured out. Isospin and strangeness quantum numbers were being discovered. But by the time this cicada emerged in 1970, a huge number of things had been transformed. In particular, there was a wealth of experimental data, and it's worth emphasizing this because, as others have pointed out, it's this experimental data throughout the 60s that eventually gave rise to the subject that we're talking about now. This is a subject which has been criticized for not having experimental data, but actually its evolution was incredibly based on data that was being discovered in the 70s. This was data on the strong interactions, when all sorts of concepts that we know about very well now were being formulated. So the idea of analyticity of the S matrix, the existence of quarks and their algebraic relations was being discovered. But my story that I'd like to emphasize is that there was a paper written by Regge in 1959 that was the beginning of what became Regge-Pol theory.
Michael, there is a request in the chat that maybe if you could come closer to the microphone.
I'll try. So
that people can hear you more clearly.
Is that any better? Hiroshi, is that better?
So, yes.
Oh, good. Okay. In 1959, Regge wrote a paper motivated, I believe, from his interest in the mathematical structure of potential scattering. He wrote a paper in which he introduced the notion of complex angular momentum. This wasn't based on trying to explain any experimental data, and indeed it didn't explain any experimental data, but it was an incredibly insightful moment where he realized that it was very interesting to define the angular momentum in the complex plane, to move away from the integers. And then, in a subsequent development, mostly involving Stanley Mandelstam and Jeffrey Chu, the Regge analysis was generalized by a series of basically of guesses to describe hopefully to describe the properties of the strong interactions. And that led to what we call the Chu-Fauci plot. So Chu and Fauci realized that if you plot the mass squared against the spin of in this case, the baryons, nucleons, you get straight lines. Of course, the straight lines are slightly obvious because those straight lines simply join a pair of points. There was very little data, and since you can always join a pair of points by a straight line, they had straight lines. But that was the beginning of Regge theory. Here is a modern plot. This is a plot of the row meson and its partners on the leading Regge trajectory for the mesons, and it is a spectacularly straight line, that is part of the whole story that developed in the 60s. And then there were crucial observations following the development of dispersion relations. There were people who formulated some rules, and in particular, there were two groups, one in Japan and one in Caltech, who formulated what became known as finite energy sum rules, which showed that you could, in an average sense, you could equate the contribution to the scattering amplitude of Reggie poles to the contribution of resonances. That you could either think of the amplitude as a sum of resonances or as a sum of Reggie poles, and that became known as duality. And that's an absolutely central feature of what happened next. It was an essential feature of the bootstrap that you don't add the S-channel and T-channel poles, you equate them. You either sum over one or the other. And I put in a note here that in a very early work, Hagedorn, essentially using the same sort of idea, came up with his with the statement that the spectrum of hadrons has to increase exponentially in order for this idea to work. And then this led to the work by Veneziano, the Veneziano model, who incorporated these ideas in this beautifully simple, absurdly simple formula, which is just the Euler beta function, essentially. As we all know, that is the origin of what happened next. And I'm going to jump over the next few generations of cicadas. Oh, sorry, before doing that, let me say, of course, I've concentrated on the strong interactions. Of course, there was work going on, incredibly important work, developing the electroweak theory at the same time, and then asymptotic freedom. But it wasn't work that had led to anywhere by 1970 that people were convinced by. And at the same time, other areas of theoretical physics involving relativity and cosmology were developing ferociously quickly as well, but they were somewhat disconnected from particle physics. So what we had was a group of subjects which were disconnected from each other, each one of which was advancing rapidly, but now we see that they're all part of the same subject. I've put in a picture here of two books that were summarized the status of the bootstrap ideas in the mid-60s. Two books with almost the same title. There's a hyphen missing in one of them. But it's worth just recording the opening lines of one of the books, the one written by my colleagues in Cambridge, which begins with the line, "One of the most remarkable discoveries in elementary particle physics has been that of the existence of the complex plane," which is, on the one hand, an absurd statement. On the other hand, it's an incredibly insightful statement, because that is what Reggie theory was all about. So let me jump quickly, and I've almost finished, to the present generation of cicadas, which has been bothering some of our colleagues in Princeton, from what I gather. This is a great-grandchild cicada of the one that came out in 1970. And he is, or she is, very impressed by the vast array of topics that have been discussed here. And I've sort of done a stream of consciousness list of these things. I'm sure I've missed many out, and each one of them has a finer grained division, which I haven't put in. But this is sort of the string theory universe. This is a set of subjects that we now talk about at string theory conferences. Why we call them string theory conferences, I don't know, because there's very little stringiness in most of these subjects, but somehow behind all of these topics is string theory. String theory has motivated the development of most of these topics. My last transparency is simply a set of questions that you've been asked to ask questions, but luckily I can also ask questions, because it's easier to ask the questions than to answer them. So I listed a set of questions which you've had circulated, I think, already. And some of them are actually questions which have arisen in the last day or so in the context of discussions by other people. So I won't read them out, but you have the list. And let me finally say once again that this has been a fantastic conference, and we are very grateful indeed to ICTP-SAIFR for organizing it in such a immaculate way. Thank you.
Thank you, Michael. So finally, Edward, can you take the turn? You are muted, Edward.
I think I had to stop the share to unmute myself. I'm sorry for the delay. So I wanted to, first of all, start by thanking the organizers for putting together such a special string conference with all the discussions and interesting talks, and also to thank them for inviting me. I, however, will be rather brief because of the fact that time is limited, but also because I'm going to only be discussing one question which I don't have an answer to, which is what is string theory? So it's actually amazing to know how much as we do about string theory, yet feel one has no little idea of what it really is. There are two useful systematic statements that capture a large part of what we know. If you wanted to capture a lot of what we know in just a couple sentences, I would personally make 2 points. One is that a classical solution corresponds to a two-dimensional superconformal field theory that has a few general properties. And the second is that quantum gravity with negative cosmological constant corresponds to a conformal field theory on the boundary of spacetime. So these statements aren't everything, but they synthesize a great deal of what we've learned in the last half century in 2 sentences. I do want to elaborate slightly on the first one, although I had some reservation. I'm doing this because I found some people looking at my slides were confused, but elaborating on it is slightly off topic, so I wasn't quite sure if I wanted to. So the statement that a classical solution is a superconformal field theory, first of all, it has an elaboration in string perturbation theory where you use the same superconformal field theory to describe quantum fluctuations. It's actually one of the most fundamental statements about string theory, but there's a huge gap in our understanding of what it means, I think, because we have very little understanding of time-dependent superconformal field theories. Everything works perfectly in a time-independent situation where we have a unitary conformal field theory times a decoupled time coordinate. But if you don't decouple time from the rest, you really have a problem because negative dimension vertex operators, e to the I k x naught, enter the game. And therefore, marginal and relevant operators can have an arbitrary number of derivatives compensated for by their time dependence. So I'm afraid we have to imagine an effective action that goes on forever with derivatives of all orders. And I'm actually personally skeptical that it really still fits in the world of local quantum field theory. And I don't think we know what kind of world it does fit into. We can't just throw away locality without something to replace it. But we don't have anything sensible to replace it. Out of desperation, I'll just mention that the TT bar deformation, we don't understand what it is, but it doesn't seem to be a local quantum field theory. It would be great if it was the prototype of a new class of somethings, which you would need to make sense of time-dependent solutions. But that's just wishful thinking. Anyway, going back to these 2 statements, they synthesize a lot of what we've learned in the last half century. And it's notable that neither of them fits into the traditional paradigm that we learned in the 20th century, where we're supposed to find a set of fields and a symmetry principle and an action for those fields with that symmetry. The reason we have trouble with the question, what is string theory, may be that the answer, first of all, is quite different from what we're used to. It doesn't fit the usual paradigm. And secondly, I suspect the answer might be more abstract than we're used to. More abstract than something in the traditional paradigm of field symmetries and action. There's another clue, or at least another fact worth mentioning, which is that our understanding of the relation of string theory to quantum mechanics has gone through several changes. Before the era of non-perturbative dualities, it was reasonable to think, or at least I, and I think many thought it was reasonable to think, that the truth in some sense might consist of finding the right new field symmetry and action, which would then be quantized in a possibly relatively conventional way. maybe using the BV formalism or something that isn't usually necessary, but in principle, following normal lines of quantization. However, the important role of non-perturbative dualities seems to contradict that idea. The theory seems to be in some sense intrinsically quantum mechanical, or at least have properties that are crucial and only come to light quantum mechanically. We don't know, we haven't made that much progress in understanding in what sense the theory might be intrinsically quantum mechanical, but possibly the current developments involving quantum information theory and gravity are leading us to a new general lesson that maybe will include a new understanding of the sense in which the theory is intrinsically quantum mechanical. Thank you.
Thank you, Edward. And I'd like to thank all the three discussion leaders for their presentations. So now I'd like to open the floor for questions, comment. Let's see, so Clifford raised hand. Let me see, yeah, I guess we can start with Clifford. Could you unmute yourself?
Hi, hopefully you can hear me.
Yes.
Yes, it's a quick question. I found, well, thanks all three speakers. It's very inspiring to reflect on our history. One of the things that struck me in Michael's presentation was his remarks about how much the experimental activity of the time actually did feed into what we now conceive of what string theory is. And I wonder whether Michael or any of the others have some optimism about what's going on now with the explosion of experimental data coming from astrophysics and cosmology and elsewhere, whether or not there could be some, you know, many years from now we reflect and find that indeed they did begin to teach us things about string theory. Is there some optimism there?
Could I just make a quick comment in addition to what I said? The point of what I said was partly that this story began, I mean, there were lots of things happening in the 50s, of course, but the story I told began with the paper by Regge, which was, in some sense, a purely theoretical paper, in which he suggested that using the angular momentum plane was interesting for certain problems in potential scattering, which were a million miles away from what happened later. So there's this interplay between Regge's sort of mathematically inspired paper and the huge amount of data that was coming in that was sort of a whole jumble of facts without any systematic organization. And really there's this rather extraordinary way in which the mathematical feature that Regge was stressing somehow fed into what happened next. And in this very roundabout way, the experimental data motivated what happened, you know, motivated in the end Veneziano's formula, which then became, of course, very theoretical again. So, of course, you know, in a sense, what I'm saying is, with all the developments that are taking place in the symbiosis between mathematics and physics, now we might hope for something to happen that would be very difficult to predict. No one would have predicted it in 1959.
If there is anybody else who wants to make a related statement, you can. Oh, okay, Andy, please.
Yeah, I think, you know, it's a really great thing if a theorist can make a prediction and it's measured and verified, but I don't think much of the stuff discovered at this conference is very close to, you know, being able to do that. But there's a much lower level of interaction that can happen, but this still is important and productive. It's just interacting with experimentalists and trying to understand what they're doing. And from my own personal experience, you know, partly because they're right next door and I'm friends with them, I've had a lot of interaction with the people on the Event Horizon Telescope, and all this stuff about the photon ring. It really has got me to, I think I've got more out of them than they have out of me. You know, it really has inspired me to think about black holes and from new angles. And it's also interesting how much you learn when you try to explain something to an experimentalist. You thought you understood it, and then you try to explain it, you know. So I think there's a much, you know, to make a prediction is too high a standard, but just to sort of interacting and indeed with the torrent of data that is, you know, we had a whole session on particle physics, but, you know, it seems to me that particle physics data is drying up, whereas astronomical data is just exploding, especially around black holes. I don't think we're going to see Hawking radiation. I don't think we're going to see R-squared corrections or quantum, but I do think that just by the process of talking to them will jog us into new ways of thinking about things.
Great. Nathan, can you unmute yourself?
So this was a question for Edward, but of course anybody else can answer too. So before the non-perturbative dualities were discovered, you had some papers where you conjectured that topological strings might provide an unbroken phase for string theory, where the broken phase would have the metric, but the topological string would somehow be a phase with more symmetry. Has that idea changed with the non-perturbative dualities, or is that still an idea that's valid?
Well, I actually view holography as a somewhat similar idea, but better. Holography, roughly I said there were no local degrees of freedom, but holography says is a boundary correction to that statement. There are local degrees of freedom on the boundary. So I consider whatever I said to have been superseded actually by holography.
Thanks.
Okay, anybody who wants to make comment in this thread?
Yes, may I?
Yes, John, please.
Yes. On this question of connection to experiment, as you know, there was a lot of enthusiasm about the possibility of discovering supersymmetry when the LHC turned on. And my attitude at the time was that I really hoped I would find it, not because I felt that it would prove that string theory was correct, nor did I feel that its non-discovery would prove that it was wrong. But it was such an exciting possibility because we would learn so much more about fundamental physics from studying the supersymmetry, that it would give us a big step up in the energy scale towards a better standard model, which would give us a better target to aim for in the reduction down from 10 to 11 dimensions.
Clifford, did you raise your hand again? Or did you want to say anything related to it? Okay, so then we can go on to Kumran.
Yes, thank you very much for interesting talks. So my question actually is perhaps directed to Edward. As you mentioned, Edward, in your talk, one of the beautiful facts that we have discovered is the duality symmetries and the importance that things are related. In fact, in my view, that's probably one of the most important things we have discovered in string theory in the past few decades. But I don't see connections between that and quantum information theory, where you hope at the end of your talk that might shed light on questions like this. I don't see any hint whatsoever up to now that that's in the card, it's in the cards in some form. Are you seeing any hints of that?
Hints of what?
Quantum information theory, what does it have to do with dualities?
Well, I only made a naive comment in my talk. Dualities, to me, were the first indication that the theory in some sense was intrinsically quantum mechanical. I think with the connection of quantum information theory and gravity, that's being explored more deeply now. And it might, I don't know if it will, but it might lead to a deeper understanding of the sense in which the theory is intrinsically quantum mechanical. That was the hope I was expressing at the end.
But not to understand dualities in some sense, because dualities, for example, relate spaces in different dimensions, and quantum information in different dimensions have completely different structures and different meanings. So I'm not sure what that is going to teach. In other words, I feel that a lot of attempts in the current developments of string theory is pushed away from answering these kind of questions that are basic questions in string theory, like what is duality? Much less effort is being devoted to deeply understanding them, in my opinion. And I just wanted to know, since you felt that the final thing is actually going in the right direction, I just wanted to see what was your take on that?
Well, my only take is that we need a different perspective. Our progress in understanding duality, we made a lot of progress with dualities 20, 25 years ago. Now we need a new perspective. Whether it will come from quantum information theory and gravity, I can't promise, of course.
I think Daniel is waving his hand.
Well, yeah, so she had this nice sort of classification of different kinds of dualities in his talk a few days ago. And so one of them was ADS-CFT duality, and certainly that one we've learned a lot from quantum information theory, Kumran. I think if you have in mind something like S-duality, then it's less clear.
Yeah, that's one of the dualities, of course, Daniel. My point is that duality is far richer than ADS-CFT. Yeah.
So, but I mean, some like in condensed matter physics, people have learned a lot of interesting things about using ideas from quantum information to study the
No, I'm not saying quantum information is not useful. I don't think it's central. That was my point.
But it's
not necessarily a central issue.
But I think understanding duality and understanding the dynamics and phases of quantum field theory are related also, right? So, I mean, and certainly
we should understand all dualities, that's for sure. We should understand all dualities, that's for sure. Duality should be understood. But to take one of them as pretty central, that's what I found surprising.
Nazi, are you raising your hand?
Yes.
Please.
I'd like to both raise a question both comment and raise a question in the same circle of ideas. It's clear that we need something which is intrinsically quantum mechanical. But it's also clear, at least to me, that time should also be emergent. And it's hard for me to imagine that these two issues are unrelated to each other. Because if time will be, I don't see how we can even think of quantum mechanics being intrinsic or not without having some pre-existing notion of time. And I don't see how perhaps the quantum information discussions will shed any light on it. But, well, I can go on and on. The short comment, I'll put some phrases: emergent time, emergent quantum mechanics, ... And I would like to hear some comments about that.
Mark, are you raising your hand?
Oh, I was just going to comment about the emergent time. I mean, I think even within ADS-CFT, if you look at time, say, behind black hole horizons, then I think that time should be understood as being emergent. It has very little to do with the time in the quantum system. So understanding that, I think, would be a good step.
Okay, Huang, you just turned on, so maybe you want to say something.
Yeah, so I just wanted to say that this connection between quantum information theory and gravity is teaching us better how to relate different objects in space-time to quantum mechanics and understanding the dictionary better. I think that's something new.
Thank you. Nadia, you are still raising your hand. Do you want to add something more? Or? Oh, okay.
I wish I had something more to add.
Okay, and we can ask Igor to turn on his microphone.
Oh, hello. I want to ask to the seniors, what are the fundamental problems of superstring theory itself from a formal point of view that you would still like to see a new look or a solution, as, for example, the equivalence between the R and S superstring and the Green-Schwarz formalism? Do we have a good description of an action which is manifestly supersymmetric and which we can quantize covariantly? Question of this nature, do you should believe deserve some new look? Can twistor theory help, or algebraic geometry?
Well, you're asking the list, so maybe we can ask others to contribute the list if there are any.
Of course, but thank you. Just for a new person coming to the field now.
I appreciate that. So maybe if there are people who wants to point out some particular theoretical directions to Okay, so Mark, you are still raising your hand and you haven't made a point this week, so maybe you can say something.
Oh, I just related to the connection with experiment. I wanted to just maybe encourage people in the field in general to maybe spend time thinking about this basic question of what could the underlying mathematical description of cosmological physics be. So it's been 20 years or well, 24 years, and we've had this great microscopic understanding of how to do string theory with asymptotically negatively curved spacetimes. And I think we're learning a lot of things, as Juan mentioned. These connections between quantum information and the bulk are teaching us, I think, a lot of the nuts and bolts of how this works, and also with the recent great progress in understanding low dimensional models. I think maybe we have a lot of good tools to sort of think about, what could the final answer look like if we had some microscopic model of cosmology, and I think that apparently it's quite constrained since we haven't found it yet, and maybe if we find it, then if you just had one example that could teach you something about, say, dark energy or some of the really basic puzzles.
Thank you. Daniel, you want to say something?
Yeah, so one of the things that seems to have been lost in, at least for many people, is the sense that, we have this beautiful ADS-CFT, but ADS-CFT thinks that, for each set of ADS boundary conditions, you have a different conformal field theory, and it's kind of lost track of the idea that these are all different vacua of one theory, which is what was hoped and maybe still expected, earlier on. And in fact, many people who work on, like students who work on ADS-CFT today, many of them, I think, don't learn supersymmetry, don't learn string theory, somehow you can get by without knowing those things, even though actually all the examples still involve supersymmetry and string theory. And so one question I had, which is maybe more concrete way of getting at this, what do we know about, say, understanding from a field theory point of view that, say, ADS4 times S7 and ADS7 times S4 have the same 11-dimensional S matrix from the dual QFT point of view? Or can we see somehow how those are related by duality to the 10-dimensional S matrix that we get from n equals 4 super Yang Mills? Is this a totally intractable question, or could there be some nice field theory way of understanding it? I mean, from the field theory point of view, it seems like a total accident, right? That they would have the same short, S matrix at high energies.
Yeah, well, so she's raising hand, but I take my position to make a couple of comments. One is that, so there are actually a couple of very interesting talks during the conference, maybe relevant to this. One is the exhibition of 10-dimensional symmetries in ADS times sphere calculation. And also another is a very interesting work by Lorenz Eberhard, where so he pointed out that actually it's more natural to consider a grand canonical ensemble summing over different ends. And this is in some way considering different types of theories. And also summing over geometry can be incorporated at the perturbative string level. So there are some hints toward the possible direction to address Daniel's questions, but a couple of others are raising hands. So start with Shi.
I just want to add to that that there's a systematic way to produce, in principle, a derivative expansion of M theory effective action, or equivalently, the derivative expansion of the gravitron S matrix in 11D from the conformal data. And in fact, some time ago, folks at Princeton, we did this for the arc of the forest, but you can, and then it was proceeded further. But the explicit check of that stopped at the order where things are controlled by supersymmetry. But that's mostly because our ignorance on the CFT side, if we were able to bootstrap, ABGM theory to more precision, then there's a hope of actually getting, the non-supersymmetry protected terms, the derivative expansion. I'm just saying that there's, in principle, a way to check that the ADS4 times S7 and ADS7 times S4 from the field theory perspective are, come from the same theory in the bulk, even though the details has not been recovered beyond the terms provided by supersymmetry yet.
Right. So of course, computing and checking is a good first thing to do, but it would be even nicer if we could somehow argue that they have to be the same based on some general CFT principles or something, including all the higher derivative terms in the action and so on.
Gabriel, I mean, wouldn't we?
Excuse me, please
sorry,
go ahead.
I mean, of course, I agree that from the what we know from the CFT side looks like a miracle, but I mean, we already have an argument. That's how the duality was proposed in the first place. So,
well, the argument is based on this idea that they're all vacua of string theory, right? So I was hoping that we could understand that more from the CFT side. I agree. It's what we expect.
Okay, Gabriele was waiting, so maybe he can.
Yes, thank you. Thank you for the three speakers. Since cosmology could be one of the places where string theory can leave its imprint, I was wondering if Ed could elaborate a little bit on his statement about time-dependent solutions, because does that mean that it will be hopeless to study the Big Bang singularities, or even what strings do inside the black hole horizons where time dependence is present? In particular, suppose I have a Kastner solution with a dilaton, which is at least to lowest order in alpha prime, it's a background. Would you expect to have problems quantizing strings in those backgrounds?
Generically, yes. So special cases like the linear dilaton makes sense. Some special things make sense. I'm actually skeptical that we have an adequate framework to understand classical solutions in strongly time-dependent spacetimes. I believe, well, first of all, I suspect that many of the younger people have no opinion on the question at all and may not be familiar with it. Among those who have an opinion, I believe the prevailing view might be that we just have a non-unitary but otherwise normal local conformal field theory. I'm actually skeptical for the reason I said in my short talk, that when you have time dependence, it looks like you have derivatives of all orders, and it looks like the world sheet theory isn't under any reasonable control. And I think that might be a sign of something important, although I've got no idea what it would be a sign of.
Well, that's certainly a very relevant point if one wants to study physics around the Big Bang.
Yes.
You don't only have, you have fast time behavior, even the derivatives are very large.
But of course, we're okay if the time dependence is slow, because then you have sigma model perturbation theory. We're also okay if the fast time dependent fields are weak, then you have ordinary perturbation theory. But for strong and strongly time dependent fields, although I don't know anything for sure, I'm skeptical that our framework is adequate.
Okay.
I think Andy is waving. Andy?
Could it be that when you study something in a time-dependent background, you have to say something about what the quantum state is? There isn't a natural quantum state. And so you have to put some extra data in to the string theory to compute scattering.
It's true you have to do that, but even in some cases that are under control, you have to do that. I think that's really a somewhat different point.
Nati, were you waving? My eyes are not very good, so I couldn't see.
I'm waiting, but it's on a slightly different topic. So I can wait if somebody.
Okay, so then in the order, Igor.
Yeah, thank you. I really enjoyed these three perspectives on string theory, and the cicadas this year were intense. I mean, this was really at the intensity frontier of cicadas, because I remember 17 years ago. But I was wondering if the three of you and other people could venture a speculation on what the cicadas 17 years from now will observe in the world of string theory. I mean, we heard about the spectrum of problems we're trying to solve. Is there any sort of guess as to what we will see, what the cicadas will see in 17 years?
Well, I would very much like to know.
You're going to tell us, aren't you, in a few minutes?
So actually, we are running out of time, but there are lots of people still. So maybe we can ask Schwarz for the last question.
This was just a follow-up on Daniel's question. It seems to me that part of the reason that the M2 brane theory and the M5 brane theory see the same space-time geometry when the space becomes big is that 11-dimensional, the completion of 11-dimensional supergravity is unique. And this is the kind of thing I think that we might hope to be able to establish somehow from low energy considerations. Some sort of uniqueness of gravitational scattering amplitudes or something like that in certain contexts. I think an easy target for this is to look for gravitational scattering amplitudes that are classical, namely that have only poles. And that space of known gravitational scattering amplitudes with only poles is very limited. And perhaps we could use low energy general consistency conditions to show that, to classify all low energy scattering amplitudes first with only poles, and then maybe more ambitiously, all gravitational scattering amplitudes in 11 dimensions or something like that, as a partial answer to your question.
Okay. So maybe Nati, do you want to make the last comment before we close this up?
I don't even know whether it's a comment or a question. Edward mentioned this way of thinking about string theory on the worldsheet with some C-hat CFT coupled to something. What is the status of strings in Ramon background, even time independent? So maybe Nathan could tell us something about that. Is this problem completely solved, or is it solved in principle? Because it's not a superconformal field theory with these conditions. It goes outside this description.
I mean, I can say that you have a sigma model where you can find a nilpotent BRST operator, and you can show that the cohomology of the BRST operator describes the physical spectrum. Can you use it to compute scattering amplitudes? Not yet. But
does this formalism exist for the most general case? Like the case without Ramon background, if it's time dependent, there is a very general description. What's the status of this with Ramon background?
So I mean, if we're talking about the pure spinor formalism, it's only defined for 10-dimensional supergravity backgrounds. So it's not, I mean, you can't describe the most general conformal field theory, but for 10-dimensional supergravity backgrounds, that you can do. And, with Cormoran and Edward, we described also ADS 3 times S3 Ramon backgrounds. And that, in some sense, is closely related to the RNS. So at least you can show how it's related to RNS when you turn off the Ramon background.
He has some comment.
I think the pure spinor formalism doesn't address the time-dependent background issue, which, as far as I understand, has to do with the fact that you can Wick rotate the worldsheet field into a theory that's unitary in the matter sector and obey the usual rules of local CFT. But I think at least perturbatively in the background deformation, this can be addressed in closed string field theory, which is now completely formulated in NSR formalism, with the PCO and vertical integration prescription. So that in principle allows you to treat time-dependent background perturbatively as a perturbative solution to the closed string field equation. It doesn't directly answer what are observable to study, but at least there's a formalism that allows you to describe what the background is and the expectation on top of that background. And also, the closed string field theory, just in NSR formalism, allows you to describe perturbatively in R flux of a Ramon background. It does not deform the worldsheet theory because the string field still lives in the same old worldsheet CFT of the original undeformed NS background, but you can treat the R flux perturbatively. It's complementary to the pure spinor formalism. The pure spinor formalism, as far as I understand, is not quite complete a level of perturbation theory due to this 1/λ bar problem, but that maybe can be, eventually resolved. Whereas the closed string field theory based on NSR can treat R flux perturbatively.
Okay, I wish we could continue going, but I think it's about time to close this conference. So before I give my own summary talk, I would like to show introduction for the next year's string conference in Vienna. So let me share the video presentation by Daniel Gruminer.
So thank you, Hiroshi, for granting me 5 minutes to talk about Strings 2022.